Hi, I'm Rob Shakir. I work in the end-to-end network architecture team at BT, which is kind of our, well, working for Neil to start with, but that's the biggest challenge. But all right, so I'm not from BT anymore. Hi, I'm Rob Shakir. And I kind of focus on our overall networks, how we're building different services, and also on some of our technology evolution, especially around IP MPLS. My background is completely in IP MPLS type network design. I worked for Pipex and for Cable and Wireless doing something on that. And I wanted to tell you about some work that we're doing kind of cross-industry with various vendors, as well as a number of other operators on evolving some of the technology that sits behind IP MPLS network, particularly in the control plane space, to be able to solve some problems that at the moment we're kind of struggling with. So I'm going to kind of talk through what are those problems and then move on to what's the solution look like, and then have a look at, with the toolkit that we're trying to build, what might we do in the future. So I'm going to start talking about just moving away from the IGP topology. So we have a really convenient set of costs in our network that we all go and program in, and it tells our network exactly how we want to route traffic. But the problem with it is we're only really looking at one optimization there. We're looking at maybe the capacity in the network, maybe the latency in the network. It really depends what the business driver for your building your network is. But we might have, say, for instance, in this network, we've got a set of links that are equal cost from how we've set the IGP metrics, but they're not necessarily equal cost in terms of overall performance. So when we want to look at, actually I want to overlay something onto my network that has a different performance requirement to the IGP topology, particularly how I would do when I'm building a shared core network, then it starts to become a bit of a problem. We want to start trying to deviate for particular services away from that topology. So we might want to do something like look at the minimum latency. So say we've got a voice signaling service. We want that to be minimum latency through the network or guaranteed particular latency. So we want to pin it to only one version of the shortest path tree. Okay, that's one service demand that we might do. Equally, we might want to do things like make disjoint services in the network. So we want to have two services where it isn't defined based on the IGP costs, how they're placed. It's defined based on the placement of the other service. I explicitly want the bottom green service, which is green, not yellow, and the yellow service at the top, which I should have picked a better color for, to be disjoint between the two within the network, and that's what the constraint is. Equally, we might have things where we've got co-routing requirements. So things like doing timing over MPLS LSPs. The 1588 timing LSP solution will try and have two services which are co-routed, so they share performance characteristics as well as share fate. So again, I want to be able to pick one version of the one version of my shortest path tree, probably only one ECMP within that topology, and not follow the IGP metric. Now, of course, I can do all this today. With RSVPTE. So I can go and build a bunch of TE LSPs that I've planned according to those particular metrics or particular dynamics and place them in the network. But the problem is then around state. And if you look at how RSVPTE, all the literature around RSVPTE scale really concentrates on steady state and midpoint. So that's looking at, okay, we've got a soft state protocol, we've created a path and a reservation state block in the midpoint, and we need to refresh it. And so there's a load of work around S-refresh, the refresh reduction extensions, which basically mean that you send one message and you refresh all of these LSPs. Great, fantastic. The thing scales when we're in a steady state. The problem happens when we have a link failure in this kind of network. And unfortunately, I have the 4 AM scars from this kind of incident. You get a link flap in the network. The midpoint sends out a path error message to all the head ends saying, hey, there's been a failure on the path that I've explicitly signaled for you, and the head end then goes and tries to resignal that path. Unfortunately, the midpoint is also quite busy at this point because he's probably doing all FRR or he's moving traffic around according to other protocols. So maybe he's got some other IGP convergence going on. All these distributed head ends, which could be hundreds of systems, then flood the midpoint with a bunch of messages saying, hey, I need a new path. You told me my path's failed. And guess what? The midpoint actually can only process a finite number of messages. So eventually it gets behind, and it doesn't. If it's then far enough behind, the midpoint, the head ends try and be good citizens, clean up the state in the network, and resignal it. Eventually, this gets to the situation where the midpoint just sits there and it's setting up LSPs constantly, but the head end's already torn down that LSP, so we never actually reach a steady state. And this this is really the scaling limit in RSVPT today. So you've got if you speak to most vendors, they'll probably not recommend that you run a PE mesh of RSVPT LSPs, but I'm talking about wanting to do it on a service scale. So my constraints were not based on the two ends of the link. They're actually based on a particular service characteristic, of which there are many, many more than there are PEs in the network. So that's one set of problems. The second set of problems we've got, I guess, is around looking at fast reroute within a network. So we've got LFA, which is really nice and simple. We look at it and we say, okay, right, I can find out someone that I can forward to who's a loop-free alternate for this prefix, and I punt the packet off to him, and he'll get it to the endpoint when I have a link failure. Unfortunately, it's really difficult to be able to offer, in each, this is very topology dependent, i.e. you have to be able to identify somebody you can forward to who will not loop the packet. And so if we end up getting to a stage where actually we're not connected to one of those nodes, so the PQ space isn't an adjacent node, then we need to set up new control plane protocols. And we end up having more and more signaling happening, control plane activity in the network to be able to get 100% coverage. When we get towards directed LFAs, then we also want to have explicit forwarding. We want to be able to tell somebody where they should forward next. So again, I need there's not a great solution here other than running lots of TLDP around my network, which isn't nice. The next one is a bit of a personal moan. This is LDP GP Sync, which I think is a really neat solution, but it's really a neat solution for a problem that we shouldn't have. So we've got an MPLS network. I'm forwarding a packet. My IGP's up, but LDP's down. So it reaches the guy who's got infrastructure LDP session down, and he doesn't have the label to be able to forward the packet. So what does he do? He bins it. That's a bit of a pain. Well, what we'll do is we'll put in this really nice fix that says when LDP's down but the IGP's up, then we increase the metric of the link such that it's not used, other than in exact backup, in completely horrific circumstances where it's the only connectivity. But the only reason we have this is because we didn't put the label forwarding information, or we split it out into from the protocol that gave us IP reachability, which really in an IP MPLS network is a bit odd. It's just really a history thing. So I've had a bit of a moan. Those are all the things I want to fix. This is probably the most tenuous acronym ever, I think. Source packet routing in networking. I wrote part of the charter for this working group, and it was named TBD all the way through, and this is what it came out as the name. It's otherwise called by Cisco segment routing, and that's probably how it's more recognized as a name. And it's really got two concepts within it. One of which is, let's put label advertisement into the IGP. And the second is it's forward based on stacked labels. So not just using a single label throughout to indicate a FEC all the way through, but stacking up multiple FECs to be able to indicate different types of forwarding. And so I'm going to kind of talk through some of the high-level concepts and not really too much into specific protocol drafts, because unfortunately I found myself slightly scarred by being an author on lots of OSPF drafts now, rather than the one true way of ISIS, but I'll get over that maybe. So we have a different set of label semantics, which are now referred to as segment identifiers. So a particular label corresponds to some form of segment ID. And those can indicate different things within the network. So this set is a node SID. So what we do is we give each node, essentially on its loopback address, an individual label, which always means through the network, this is the shortest path towards this device. This is kind of a special case of a prefix label, because we're saying it's a unique identifier for a node. It's used by everybody. But really, you could use this for anything. Everybody understands the algorithm that's used to compute the semantics of this label, but it'll always get me to a particular resource. The next type of label we have is we've got nodes, so now we've got adjacencies within the network. So we've got have a local label allocation, so it's just allocated by the device that's sitting on the end of the link to say an adjacency that's within the IGP. And this really gives you an explicit way to be able to say, I want to forward a packet down a particular link, or a particular set of links. Because instead of having a single reservation that goes over one link like we would in RSVP today, we can put the same label on a bunch of links that are all ECMPs to the same device on the other end, and then you immediately have an ECMP-aware way to do forwarding between those two nodes. The third type that I'll talk to is a prefix SID, which is just as I said before. It's something that's in the IGP topology that we assign a label towards, but we isn't necessarily going to allocate it itself. So if you imagine it's a leaf prefix in the IGP, it might be a management station, it might be some other node. And then the fourth type, and I've kind of included this just as an indication of what more we can do with it, is looking at how we might indicate reachability to certain types of resource. So in this case, so imagine we've got a dual plane network, we've got a red plane and a blue plane, and we want to be able to say, a head end wants to be able to say, I want to forward to that device over there, but I want to follow the blue plane. In this case, we could advertise this label that means when you get this packet, forward it down the blue plane. And it's an anycast label because every entry point to the blue plane would advertise this and be able to use it as a forwarding semantic. So how do we actually end up with forwarding? If we take the really basic case that I've got one node in the IGP that wants to forward to another node in the IGP, then each node advertises its node segment identifier, and that's the global label that means you can reach me. So the head end imposes that label on the packet, and then at each stage we've defined, there's an abstract forwarding model defined for segment routing that's not really related to the underlying data plane, but in this case I'm going to only talk to the MPLS one. So each of the nodes along that LSP have now programmed in that they just, for this label, all they do is swap it for itself. It's a continue operation, and so to get traffic from one end to another, I just impose the label that says get to that node, and off it goes. It's there, it gets to the other end. Immediately now, I can get rid of LDP if I wanted to, if this is the only type of traffic in this network, and I don't need LDP IGP Sync anymore, because if my IGP falls over, the label goes away. No need for any kind of linking together of two particular protocols. So that's kind of boring. That just gets us forwarding through the network. Maybe it kills one of my moans. But the other thing we can then do is, because we've got these identifiers on a per node basis, we can start to define things like reroutes around particular devices without having to do anything too complicated in the middle. So let's say that this P1 to P2 link has become congested. And I can see this, and I want to be able to say, right, okay, actually my P1 to P3 and P3 to P2 links are actually really quiet. To be able to do that kind of forwarding, that detoured forwarding, we can now just impose two labels at the head end, which say, the first one saying 102, which says go to P3, and then the second saying 64, which says then go on to the tail end. And we didn't need to make any kind of reservation on the middle boxes. Actually, we didn't really need to do anything. They didn't have to be running a new protocol like they would have done if we'd maybe had RSVP-TE previously. And we've managed to relatively simply make that kind of detour through the network. If we then move on to looking at how does this help with IPFRR, then actually we get to really quite simple set of instructions that give us one way to be able to solve this problem anywhere. When we've got an LFA, we don't change anything, we just punt the packet at the guy who is the LFA and off it goes. When we've got a remote LFA, which previously we needed to run control plane protocols for, we just push the label that gets us to the PQ node, and he's then our repair point. And when we get to a directed LFA, which is where there isn't a P and Q node, then there isn't a single intersection between the P and Q spaces, then we can push a label to P with the forwarding instruction that then says go to this Q node. And actually there's some work gone on in Cisco, which Pierre Francois led on, around showing that for any network with a symmetrical set of metrics, so metric from A to B is the same as metric from B to A, then we can solve any topology with FRR. And there's no need for new control plane. There's not a scaling impact here now. We've enabled it within the network. You could only be using these labels for this particular purpose, and we've now got what looks like 100% coverage for FRR without needing to have RSVP-TE. Then looking towards that first set of questions, or first set of problems that I looked at, around how do we do explicit forwarding or deviate away from the IGP topology, then because of the adjacency segment identifier, we can actually do that relatively simply. Each link now ends up with a label that's indicating it, and is programmed at each hop as a pop operation with a specific next hop. So if we look at, say, this SID 301 just here, P3 programs into its FIB that it's allocated that as a local label, it's advertising it out, and when it receives, it pops the label and it pushes it towards, the next hop is now P4. So what I can now do is build a stack of labels that, to make this wiggly path through the network, then I push 201 to get on this particular link, and then 301, and then 401, and then 501, and I can choose an arbitrary path through the network. Now, all the state is now here. The head end now knows where he needs to push the packet to, not anyone in the middle. No one's had to make a particular reservation for it. This isn't a wholly good news story, because now I've got 4 labels rather than 1 on this packet, and there's some limitations in terms of how many I can push, how many a midpoint can hash on, but I haven't got any situation now which is wholly unrecoverable. Either the midpoint can hash or the head end can push, or he can't. There isn't a situation where something falls over and then my network might not recover again, which is always a bad day when that happens, right? So this gives us the logic to be able to impose these arbitrary forwarding paths through the network. But we still have the problem of how do we actually work out which segment identifiers we're going to use? And there's really kind of two approaches for this. Now, I've written a draft in the IETF to try and describe it. One is that we go and we use exactly what we've got for TE today. So the process today is I want to get to this tail end. Can you give me a path according to these particular constraints? Some CSPF daemon goes away and he runs that, and then he pans on to RSVP to say, here's my ERO, please signal it. Great. We can reuse exactly that, other than just stop handing the ERO over to RSVP, and rather just look in the IGP database and work out what the labels you would need to make that path are. And you can actually do some compression to say, well, actually, this bit's along the shortest path tree, and this bit isn't, so I only need to use a new label where I need to deviate from the shortest path tree. It's great where the IGP TED, we've actually got the visibility of the whole IGP. If we start to look at multi-area scenarios, or even if we look at some of those situations like a co-routed LSP or disjoint LSPs, then one head end doesn't have the information. There is no situation in which the head end has all the information about the placement of the other service. So some approach where we use an external path computation element, great, we already have it for RSVPT in terms of a set of standards, not so much in terms of deployment, but giving that PCE some way to be able to compute the segments or learn about the IGP database and the topology of the network, and then the client head MPE to be able to make a request to it to say, hi, I want to get to this particular device, and with these particular constraints, please can you give me a way to get there? Rather than giving him the ERO to go and send off into a path message, then we can just give him the segment stack. And great, he imposes the segments and off he goes. But this PCE type approach then becomes kind of interesting. We need to give it a bunch of different things. And again, there's a slight caveat of my removing state thing here, because the PCE is going to need to be stateful to be able to do things like outside of the area, there's a link failure, and my head end never gets any notification unless he's running some active OAM along the LSP. So the re-optimization needs to be triggered by the PCE. So we have this device, but we can start to give it, so it's got some state about that, but we can start to give it more information. We can give it topology information about layers that are below it. So for instance, I can have, rather than having to try and get all my SRLGs from my optical network into my IP MPLS network, then I can give my PC some access to some form of event tree, some form of existing model, and then great, I've now got a way that I can do optical SRLG disjointness as well as just in the MPLS network. There's a whole kind of interesting problem space around here, which the 3 letters SDN are coming horribly close to, and I'm going to avoid them completely, to say, well, actually, I need some way that I can ask for a path in a way that says it's got this particular set of constraints. I need to be able to learn about what the network's like. Maybe I need to learn about LSP placement if I'm trying to do things like use RSVPT LSPs that are forwarding adjacencies in the topology as something that I can apply as part of the forwarding. And maybe I need to know something about utilization. So, whoops, this is feeling very SDN. But this bit here and the whole PCEP bit is something that's been there for a while. It's been there as part of RSVP. Although we might want to look to extend it to say, and there is work going on to extend it to say, actually, how do we create paths from the PC rather than have to create them on the head end? And how do we create FECs that tell us how to forward down it? And so, what could we do with this? So let's say I've built this box. I've built my PCE, and it's sat there learning all this about my network. Can start to use it to actively interact with my topology. So let's say we get some alerts saying, hey, look, the link utilization on this X to Y link is now over 80%. You might care about this. This device has now got visibility of utilization in the network. It's got visibility of the global resources, the overall network topology. So it can start to look at, well, what could I do? What if I went and added this TE-LSP over here or this SR-LSP over here to be able to route away from it? And let's say it figures out a way that it can move 2 head-end flows, and that will alleviate the risk or the congestion that's occurred in the network. Again, with the LSP creation and the FEC creation, he could go and do that. And there's no real scaling limit about this. At the moment, you'd probably be a little worried about this because how many of these LSPs are you going to end up with? What's the midpoint scale that you end up with? How much computational resource does it require? But using SR, we avoid that problem. And meanwhile, maybe the guy, my NOC engineer just here only just got the text message about it. So you could have automatically made these kind of changes before there's really a problem in the network. Not sure this is really going to happen, but it's a tool. If I take the toolkit that I think you might want to build for solving some of those initial problems, it looks like a way that you might want to move forward. So, cool. I'm hoping I didn't fly through that too quickly because I haven't actually ever done it in 25 minutes when I talk to myself. So let's hope I was slightly clear. But any questions, much appreciated.
Hey, Matthew Walster from LMAX. I'm just wondering what your kind of transition strategy is going to be. If you're applying this onto the top of your normal SPF algorithm, how are you planning on rolling over to it? Is it just going to be another run of CSPF within your router that's going to do it, or are you just going to leave that to the implementation?
So there's various transition strategies. We're doing some work which makes ours a little easier, for in the core of the network anyway. But there's 2 ways. You start to roll the code out that supports it, and then you've at least got the labels there. The problem tends to be when the difficult bit comes where you've got bits of the network only do LDP and the bits of it that do SR, and there's actually a mapping server type approach that I'm not even going to attempt to explain just here because it took me at least 3 goes through it to understand it, so I'm not really sure I can represent it fairly. But in the SR use cases draft, or there's an SR LDP working draft in the IETF, in Spring working group, that describes how you would do that. Essentially, the mapping, an element in the network advertises proxy labels for another device that doesn't have this capability, and each border node does a swap onto the LDP label. It kind of stitches an SR FEC onto an LDP FEC. Okay,
and the other part of the question really was one of the key reasons why we use RSPF is fast failover and stuff like that. Are you going to see RSPF kind of dying, RSVP dying, or are you actually going to kind of see it still having its sole market?
Well, I mean, it sort of depends how far. Well, it depends which vendor you work for, I think, actually. There's some religion. And the other bit is probably around can LFA and the policy LFA type stuff that's going on, especially led by the France Telecom guys, can that really meet all the requirements? So that having an LFA is just fine, but having an SRLG disjoint LFA and all these things, we've kind of come up with a lot of policy things about, well, you wouldn't want to go via this device. This device is an overseas PE, so it's probably not a good LFA, and those kind of things. So I think we're getting there. And at that point, I can't see why you would deploy RSVP unless you want CAC, basically. You want to be able to admit LSPs based on bandwidth, because SR removes all the state from the midpoint. So the midpoint doesn't know what LSPs go over it, so it now can't say, well, actually, this link's full. That's part of the reason you end up needing some of the PCE functionality. But then you can make a choice between, do I want this in the network, and for this set of LSPs that are going to have bandwidth reservation on them, or do I want to do that out of the network? So I don't think it'll die, but there will certainly be alternatives to deploying it.
Cheers.
Hi, Rob. Thank you. That was a really interesting presentation, and I wish I'd paid more attention to the progress of this work so far. So I've got 2 questions that might actually be obvious to people who know more about this. Throughout the presentation, you referred to MPLS data appearing in the IGP, but not an IGP in particular. Or is this because it's expected to work with everything that people typically use today, or are you expecting to build a new IGP which is optimized for
No,
MPLS?
so it'll be in both ISIS and OSPF. So ISIS is really nice because we just go and add a TLV. OSPF is painful because we don't, and we go away and do things with LSAs and blah, blah, blah. But that's been done, so it will be there in existing IGPs, so there'll be no need for a new one.
Okay, and is this work at a mature enough level that means you've actually seen an implementation, and if so, how do aggregated links perform, or multiple paths between the same two P devices perform from a load sharing point of view with multiple labels or extra labels in the path? Because that's been a way that load sharing has been hacked in before. And does this work mean that we've got a big grey nasty hashing cloud that we don't know how to solve yet?
It depends on what the hardware does, basically. I can't really comment in too much detail because there's probably a few NDAs that I'm under there. But it doesn't look impossible. It looks impossible if you try and do everything on every packet at the same time. Like one vendor said to me, well, you know, we couldn't do PBB at the same time as this. And it's like, well, that's fine. I don't want PBB. That's actually a bonus. Remove it, please. But it will work in terms of hashing. It's just how deep, how well will it work is still not clear because I don't think we've tested it yet. We've been working on this for maybe, I guess the Cisco guys have been working on this longer. Mark can nod at that, I think. I've been involved in it for 18 months, and there are 2 versions of code that are out there that if one is in the right EFT program or has the right contact in a vendor, you could get.
Great. Thank you.
Thank you, Rob.